Good evening, all. Today we are here for the fourth problem solving session for the course Spectroscopic Techniques for Pharmaceutical and Biopharmaceutical Industries. I request all of you to switch off your audios if you don't have any question to raise. Um, yeah, please switch off your audios if you don't have any questions. Okay. I'm sorry, I'm getting a background from someone. Can you, if you have any question, please raise it up. Otherwise, please switch off your audio. I hope I'm audible to all of you. If I'm audible, can you leave a message in the chat box? One of you can just leave a message in the chat box. That's good enough. Yeah. Thank you. Thank you. Yeah. Okay. So we are starting with our first question for this particular week. So this time we have been asked to. This time we have been introduced to vibrational spectroscopy and Raman spectroscopy and all. So we are dealing with a couple of questions pertinent to vibrational spectroscopy. So yeah, the first question is to find the frequency of vibrational transition given a force constant. So we are looking at this particular molecule Hi. So we have been given what is the Kex. Sorry, not Kx. Sorry, K. The force constant K for this particular bond. So this is equal to 3.1 into 10 to the power 5 dyne centimeter inverse. So 1 dyne centimeter inverse is equal to 1 gram centimeter second inverse. So this is going to be 3.1 into 10 to the power 5 gram second inverse. Okay. So we have been asked to find what is the frequency of transition. So we know that for the frequency of transition for from ground state V is equal to 0 to V is equal to 1 is the energy gap between this. So the frequency of transition between V is equal to 0 to V is equal to 1. So from the ground state to the excited state. So what is this omega OSC is what we have been asked today. So this is equal to 1 divided by 2 pi c root of k by mu, where k is the force constant which is given by this, mu is the reduced mass, so c is 3 into 10 to the power 10 centimeter second inverse. This is the speed of the light. Now we have to find what is mu for Hi. So mu is going to be m1 m2 divided by m1 plus m2. So m1 here is for H, it is 1 MAU, it's a AMU. For iodide, it is 127 AMU. So this is going to be 127 into 1 divided by 127 plus 1. This is 127 divided by 128. This is an AMU. So we have to convert 1 AMU to kilogram. So 1 AMU is equal to 1.66 into 10 to the power minus 27 kilogram. We have the force constant in grams second inverse, so we can convert this into grams. So this is 1.66 into 10 to the power minus 24 grams. So 127 divided by 128 into 1.66 into 10 to the power minus 24 grams. So let's calculate that. So it's 127 divided by 128 multiplied by 1.6. This is equal to, sorry, it's equal to 1.647. 647 into 10 to the power minus 24 grams. Okay, so this is mu for HI. And now what we have to do is we have to find what is omega OSC. So we know in the question it has been given what is K. We have found what is mu. C, we know what is the speed of the light. We can just calculate what is the omega OSC, which is the vibrational, the frequency at which the vibrational transitions happens. So omega OSC is equal to 1 by 2 pi c root of k by mu. So this is 1 divided by 2 into pi into c is 3 into 10 to the power 10 centimeter second inverse. Square root of k is this should be second square. 1 second. There is a correction in terms in case of dying. So sorry. Sorry about that. Oh man. Okay. We have lost what we have been writing all the while. Okay, let me just quickly recap whatever we have been writing. So we have told that we are looking at HI, and we have been given what is K, force constant K, that is 3.1 into 10 to the power 5 dyne centimeter inverse. So 1 dyne is equal to 1 dyne is equal to gram centimeter second inverse. let's say second square inverse. Sorry, this is the correction that I wanted to make. So this is going to be 3.1 into 10 to the power 5 gram second square inverse. And we have calculated what is mu. Mu was 127. Sorry. Mu was m1 m2 divided by m1 plus m2. So this is going to be this is going to be 127 into 1 divided by 128. This much AMU. 1 AMU is equal to 1.66 into 10 to the power minus 10 to the power minus 27 kilogram. This is equal to 1.66 into 10 to the power minus 24 kilogram. Grams. And while we are converting this AMU to grams, this comes to 1.64 into 10 to the power. Okay, basically 127 by 128 into 1.66 into 10 to the power minus 24 grams. So this come to 1.64 into 10 to the power minus 24 grams. And yeah, so this is where we were, and now we have to find what is the, we are looking at V is equal to 0 to V is equal to 1 transition, and we are supposed to find what is omega OIC. So omega OIC in centimeter inverse is 2 pi c into root of k by mu. Sorry. Okay. So where this is 1 by 2 pi into 3 into 10 to the power 8 centimeter second inverse. So the value of C is 3 into 10 to the power 8 meter per second. So this is same as 3 into 10 to the power 10 centimeter second inverse into root of K is 3.1 into 10 to the power 5 grams second inverse square divided by 1.64 into 10 to the power minus 24 grams. So let's do the calculation. 3.1 divided by 1.64 is 1.89. Square root of 1.89 is going to be 1. So this is 10 to the power minus 24. 10 to the power minus 24. When it comes to the numerator, this will become 10 to the power 29. 24 minus 24 will become plus 24 when it comes to the numerator. Adding with the 10 to the power 5 already, which was already in the numerator, it will become 10 to the power 29, and these 2 grams will go off, and we'll have second square inverse here. And we have to take a square root of 1.89 into 10 to the power 29. So that will become square root of 1. So 4.34 into 10 to the power 10 to the power 14 second square inverse. Square root of second square inverse will become second inverse. So we have to divide it by 2 pi into 3 into 10 to the power 8 centimeter second inverse. These two will cancel out. So this one divided by 2 into 3.14. This come to 0.2307 into 10 to the power 6 centimeter inverse. Okay. I'm getting something like there is some correction in terms of what I'm getting. When I'm doing the calculation right now, I'm getting something like 2 orders of magnitude different than what I should actually get. Let me just figure out. So okay, that is because this should be 10 to the power 10. Sorry, that much centimeter second inverse it is. I have written the value for meter second inverse. Sorry about that. Yeah. So multiplied by 4.34 into 10 to the power 14. So this will become 10 to the power 4 centimeter inverse. This will become 2307.6 centimeter inverse. So this is the frequency for the transition from V is equal to 0 to V is equal to, from V is equal to 0 to V is equal to 1. Now the second part of the question is to find what is the frequency at which this occurs for DI. 1 second. Yeah, we may need a slide to explain that. So we know that omega bar OSC is equal to 1 by 2 pi c root of k by mu. Between HI and DI, we are assuming k doesn't change, because in general the electronic environment is going to be sort of similar compared to which actually determines the bond strength and the bond strength. We are sort of assuming that k is going to be almost similar for HI and DI. So KHI is approximately equal to KDI. So which basically tells us omega OSC is directly proportional to 1 by mu. So we omega bar OSC for DI by omega bar OSC for HI is equal to root of mu of HI divided by mu of DI. Now we know what is mu of HI. 1.64 into 10 to the power minus 24 grams. Now we have to find what is mu of DI, and we already know omega bar OSC of HI is 2306.6 centimeter inverse. So reduced mass of DI we have to calculate. So that is M1 M2 divided by M1 plus M2. So this is 2 AMU, whereas this one is 127 AMU. So 2 into 127 divided by 127 plus 2, this much AMU is going to be the reduced mass. So this will be 127 into 2 divided by 129 into 1. So we have to convert this to grams. So this will be 1.66 into 10 to the power minus 24 grams. So this is going to be 3.268 into 10 to the power minus 24 grams. So so we have to find what is omega bar OSC of DI. So this is equal to root of mu of HI by mu of DI into omega bar OSC of HI. So this is equal to 1.64 into 10 to the power minus 24 divided by 3.268 into 10 to the power minus 24. Both of them are in grams, so it's going to cancel out, and we have 2306.6. Yeah, sorry. So let's do the calculation. This is root of 1.64 divided by 3.268. That's 0.7084 into 2307.6 centimeter inverse. So this is going to be 1634.7 centimeter inverse. Yeah, so this is what how omega bar OSC when it is when the frequency of transition will be 1634.7 when it is DI. When it is HI, it is 2307.6. So this is what we have been asked to find in the first question. So the second question is to find the relative population of the first excited state of a vibrational energy level, which is relative population of first excited state, which is V is equal to 1 with respect to the ground state, which is V is equal to 0. And we have to find it at two different temperatures, at 298 and 373. This is basically 25 degrees Celsius and this is 100 degrees Celsius. Yeah, so sorry. So it depends upon how many number of molecules are present in V is equal to 1 versus V is equal to 0. So this is going to be e raised to minus delta E by kBt. So here delta E is going to be Hc nu bar. So we have been given the vibrational frequency, the wave number at vibrational frequency. So this is going to be Hc nu bar. This is in centimeter. Sorry. Yeah. So we have to find what is delta E by kBt, where it is Hc nu bar divided by kBt. Kb is the Boltzmann constant and it is 1.38 into 10 to the power into 10 to the power minus 24 joule Kelvin inverse. And yeah, first thing is at 298 Kelvin, how much is delta E by kBt? So that's going to be 6. H is 6.626, which is H is Planck's constant, and it has a value of 6.626 into 10 to the power minus 34 joule second. C is 3 into 10 to the power 10 centimeter second inverse. Nu bar is 1000 centimeter inverse divided by kb is 1.38 into 10 to the power minus 24. T is 298. So let's do the calculation. It is 6.626 into 3 divided by 1.38 into 298. This is 0.048 into, so it's going to be 10 to the power 3, and this is joule Kelvin inverse Kelvin. So at the end we are going to cancel out all the units. So joules will cancel out, centimeter inverse cancel out, second inverse and second will also cancel out. So we'll have 48.3 is the value here, and now we have to find what is the NV divided, it's NV is equal to 1 divided by NV is equal to 0. So this is going to be e raised to minus 48.3. So if you do the calculation, you will get 'I'm getting something like 1.05 into 10 to the power minus 21, but I'm supposed to get something like there is again some error with the power, 10 raised to power calculation. I don't know how it has come. It's supposed to come as 8.22 into 10 to the power minus 3. So it was basically, this answer is supposed to come out as 4.83. So this is something which I have gotten as wrong. I don't know where I have messed up with the power calculation. I think this is 10 to the power minus 23 rather than 10 to the power minus 24. I think that's where the mistake is. I'll check what is the exact power for kBt. If um, kb, I think it is 1.38 into 10 to the power minus 23 instead of 10 to the power minus 24. I'll check and get back to you in the next tutorial. Yeah, otherwise this is how the calculation follows. And when you have to at 373 Kelvin, we can follow the same calculation. Instead of 298, you can put in it as 373 and find the value. Yeah, 1 second, let me see whether I have the correct value of kBt. No, I don't think so. I have it at this point of time. But I think this is the mistake. You have to put value of kb as 1.38 into 10 to the power minus 23. Then we are supposed to get the delta E by kBt at 298 Kelvin is going to be 4.83, and using which if we substitute that in this particular equation, we'll get what is the relative population, and the relative population is supposed to come as 0.0082 at 298 Kelvin. Okay, for at 373 Kelvin we can do the same calculation just by substituting. So in this particular case, delta E by kBt is equal to 6.626 into 10 to the power minus 34 into 3 into 10 to the power 10 into, so this 10,000 I can write as 10 to the power 3 divided by 1.38 into 10 to the power minus 23 into 373. Okay. So this will come as 3.86, and now then we can find what is NV by NV equal to 1 divided by NV is equal to 0. This will come also something similar like this. So this will be 0.02. This is at 373 and this is at 298. At 298 it is supposed to come at 0.0082. You have to resubstitute kb as 1.38 into 10 to the power minus 23 for this particular calculation, and you will get the value as 0.0082. Okay, so let's go to the next question. So the next question is about rotational 5 rotational energy levels in HCl, and we have to find what is the frequency of oscillation, which is omega E or omega OSC, and what is the unharmonicity constant, which is Xc. So frequency of oscillation omega E, unharmonicity constant Xc. So for every energy level when there is unharmonic oscillations, EV is going to be omega E V plus 1 by 2 minus V plus 1 by 2 the whole square omega E X. Okay, the other thing is so in this particular set of, in case of unharmonic oscillation, so if this is V is equal to 0, V is equal to 1, 2, 3, 4, you can see the energy gaps going lower. So if this is E, this is R. Okay. we can see that anharmonic, when we go to the anharmonic limit of vibrations, we can see that the energy gap is no longer, the energy gap between the levels are no longer uniform. We can see that it reduces, the energy gap reduces as we go higher in V. Okay, so this is clearly when you actually, sorry, yeah, when you actually look at these energy values, you can clearly see that the energy gap is going to be lower down as we increase the V values. So let me pictorially, no, I'm just representing it as here. So this is 81.86, this is V equal to 0, V equal to 1, 4367.50. This is V equal to 2, and so on. So you have V equal to 3, V equal to 4, V equal to 5. So we have been given all the energy, first 5 vibrational energy levels of HCl. Okay, so we have been asked to find what is omega E and Xc. So I am using E is 0, E1 and E2 to find it. There are a couple, so basically we need so in this particular equation, so if we have omega E by 2 minus 1 by 4 omega E Xc. So in this particular equation you have two unknowns, which is omega E and Xc. To solve this we need at least two equations. So this will be 3 omega E by 2. This is 9 by 4 omega E Xc. So basically you just need E0 and E1. I'm just writing down E2 also. You can use E2 or E2 and E1 to solve this, to solve the these two equations to find out omega E and Xc. Or you can also use, you are also free to use E3, E4 or E5. Any of, you won't have till E5. Yeah, you are free to use any of these five um, energy equations to solve it. So we know E0 is going to be 1481.86. This is equal to 4367.50. Yeah, so what we can, this is equation 1 and this is equation 2. So what we can do is, one second. Yeah, so what we can do is we can multiply equation 1 with, okay, let me rewrite the equation 1 in the next page. So we have omega E, sorry, omega E by 2 minus 1 by 4 omega E xc is equal to 1481.86. 3 omega E by 2 minus 9 by 4 omega E xc is equal to 4367.50. This is equation 1. This is equation 2. So we can multiply equation 1 with 3. So basically this will become 3 omega E by 2 minus 3 by 4 omega E xe equal to 1481.86 into 3. So this is 1481.86 into 3 is 4445.8. Okay, so this is going to be equation 3. Now we can negate equation 3 minus 2. So this will make it 2 omega E minus 3 omega E by 2 minus 3 omega E by 2. That will go to 0. Minus 3 by 4 omega E xc minus of minus 9 by 4 omega E xc. So that will become minus 3 by 4 plus 9 by 4 omega E xc 4445.58 minus 4367.50. So this will become 6 by 4 omega E xc. So this will become 08. Now we can find what is omega E xc. So that is 78.08 into 4 divided by 6. So into this is 52.05. So omega E xc is going to be 52.05. So this is going to be equation 4. What we'll do is we'll substitute 4 in 1. So omega E by 2 minus 1 by 4 omega E xc is going to be 52.05. That is 1481.86. So omega E by 2 is equal to 1481.86 divided by 1481.86 minus plus 52.05 divided by 4. So this is equal to 1494.87. So omega is 1494.87 into 2, because this 2 in the denominator, when it goes to the other side, it will become multiplied by 2. So this one multiplied by 2 is 2989.74. So the omega E is going to be 2989.74. Let me insert one more slide. Yeah, so yeah, I can do it in the top, no problem. So we know what is omega E and we know what is omega E XC. So let's substitute. So we know omega E XC is equal to 78.08. So we know what is omega E. So XC is going to be 78.08. Sorry. No, this is 52.05. Mistook it. Divided by omega E. Omega E is given by we have solved what is omega E. So substitute that 52.05 divided by 2989.74. So this is 52.05 divided by 2989.74. So this is 0.0174. And the unit for XC doesn't have any particular unit as far as I know. You are free to correct me if I'm wrong. Yeah. So this is the unharmonicity constant 0.00174. So our omega E is 2989.7 and our XC is 0.0174. Right? Now we have been asked to find what is the dissociation energy for the molecule. So what does it mean by dissociation energy? So for an unharmonic oscillator, for a molecule which is, if you are looking at a molecule where this is M1, M2, which undergoes an unharmonic oscillation with the 0 point energy V, with V is equal to 1, V is equal to 2, 3, 4, things like that. So where this is C and this is R. Okay, so let me see whether I can use a different color. Yeah, so at energy at V is equal to 0, which is E of 0, is 0 point energy. So energy of this particular level is 0 point energy. And so you have a maximum energy at which, after which the molecule won't the bond won't be there, which basically means we are going to break this bond. So if you have a bond like this, and if it is going to vibrate, if it is going to vibrate like this, and after a point of after a point of time, this is going to break apart, because we are taking the two molecules, two atoms which forms the bond, to a distance where it can't share the atomic orbitals to form the bond itself. So that's where we are saying that the bonds are going to break after a point of after a point of time. So this happens at a particular V, which is called V max. So this happens when the oscillations are unharmonic. So this Vmax calculation has been done in the class. I'll just give you a brief explanation of how the calculation is done. I won't be doing the calculation per se at this point of time. So basically, Zero point energy, I already have defined what is zero point energy. Zero point energy is the, zero point is energy is the energy of the molecule when V is equal to 0. So the next thing is going to be the next thing is going to be what is it? Dissociation energy. So dissociation energy is what we have been asked to calculate. So dissociation energy is equal to dE minus E of 0. E of 0 is the 0 point energy. dE is the energy at which V is equal to V max. So this is dE, this is E of 0, and dissociation energy is D0. Okay, so dissociation energy is the energy gap between the energy of the molecule at the maximum value of V and the 0 point energy. 0 point energy is the minimum energy at which the minimum energy, the energy at energy of the system at V is equal to 0. So how do we know what is dE? So what is how do we know what is V max? So let's start the question from where, how to find what is. So if we know what is V max, we can put it in the we can put that value in the formula to find the energy of an anharmonic system, which is V plus 1 by 2 omega E minus V plus 1 by 2 omega E xc. So this is the energy of the system at V is equal at a particular V value when it undergoes anharmonic oscillation. Now we have to find what is V max. So we find V max by equating dE by dV is equal to 0. So we basically have to differentiate. Okay, this equation, let me name it as A. So we have to differentiate the equation A with respect to dV and equate it to 0. So from which we'll get a value for V. So that is going to be V max. And in the class it has been I don't think so sir has also solved it per se. He also has told how it is being done. If you have any problem, we can try differentiating it now. Otherwise, you can try differentiating by yourself. You will definitely get Vmax values 1 by 2xc minus 1 by 2. Okay, so we'll know what is Vmax. If you substitute that particular value in E, you will get dE value. And if you substitute and do all the calculation, you will get dE as omega E square divided by 4xc omega E. So if you substitute Vmax to V to 1 by 2xc minus 1 by 2 in equation A, which is this one, equation A, we'll get, so this is E, V is equal to Vmax. So this is equal to D. And we need to find what is E0. E of EV is equal to 0, or this is equal to E of 0. This is omega E by 2 minus omega E xc divided by 4. So from since we already know what is omega E and Xc, we can calculate the dissociation energy. So dissociation energy D0 is equal to dE minus E of 0, where dE is equal to omega E square divided by 2Xc omega E. E of 0 is equal to omega E by 2 minus omega E Xc by 4. How did I get EV is equal to 0 or E of 0 is just by substituting V is equal to 0 in equation A. So D0 is equal to, by putting in all the values, so this is omega E square divided by 2Xc omega E minus omega E by 2 minus of minus omega E Xc by 4 is plus omega E Xc by 4. So let's substitute it. Two 2989.7 into 0.0174 divided by 4. Yeah. Okay. 2989.7 square divided by 4 into 2989.7 2989.7 divided by 2 plus 2989.7 I'm getting something something is negative value, which shouldn't be the case. Yeah, I don't know what is the sort of mistake that I have done here. Yeah, omega Axc, you can either put this value in, or yeah, it's fine. This one we can negate, so this is 2989.7 divided by 4 minus 2989.7 by 2 plus, yeah, as you say, yeah, someone has told that it is 52.05. Yeah, from the previous calculation that we have done, it is 52.05. Yeah, but still this won't come out to be the value that uh, to the value that it should be. I don't know where did I make the mistake. Okay, I don't know why did I 0.0174. 2989.7. Okay, fine. Yeah. Okay. So here I have made a mistake by putting it as 2. This should be 0.0194. So if you divide 2989.7 by 2 into 0.0174 and negate it by 2989 divided by 2, divide by 2, and you have to add it with 52 omega exe. This one will come to 52.05. So 52.05 divided by 4. And what I'm getting is 8442.9.08 centimeter inverse. Yeah, which is sort of believable, because your Vmax is going to be 1 by 2 Xe minus 1 by 2, right? So that is going to be 1 divided by 2 into 0.0179. Oh, sorry, 174 minus 0. So this is around 28. So yeah, we are looking at V is equal to 0 versus V is equal to 28. And this much energy gap is sort of expected in this particular case. Let me just quickly explain the one last question about the IR spectrum of biomolecules. So it is about, so we have been introduced to various IR specific bands in protein. So I'm just, the first one just gives what is the nu bar, the wave number. Second one, what is the type of the IR motion, and this is the name of band. So we have been just asked to do a match the following, match these three sets of match these three sets. So this 3510 centimeter inverse corresponds to the nth stretching, which has been called as amide band A. So it is going to be this way, and something which is between 1600 1700 centimeter inverse, this corresponds to CO stretching, and this has been called as amide 1 band. And the peak that comes between 1500 and 1550 is due to NH bending, and it has been called as amide 2 band. With this, I would like to end the session for today. Let me know if you have any particular questions.